Hi, I'm Zach with HKN. Today we're going to solve a circuit that has a capacitor and an inductor in it. And anytime you have a circuit like this, it's called a second order circuit because our differential equation that we're going to come up with has a second derivative term in it. So we're just going to go through how to get this. Now, sometimes you'll have a circuit where your inductor and your capacitor are either perfectly in series with each other or perfectly in parallel. In those cases, there's some formulas you can use to make the process a little bit quicker. But in this circuit, we can see that they're not going to be either in parallel or in series. So we're going to go through the process of writing down a differential equation and solving it. So we are going to solve the differential equation for this voltage right here. So we can see that the voltage across our resistor and the voltage across our capacitor are the same voltage. Now, usually when you have a second order circuit, you're going to want to work with a value that's common to like a couple of your elements. So you can see this voltage is common to these two elements, so we're going to work with that. Now, we can say right off the bat, VR is equal to VC is equal to what we're going to call from now on V1. And that is the voltage of this node right here. Okay, so we're going to want initial conditions. It's better to solve for more initial conditions than you need than less than you need, so we're going to solve for a few things. We know that we'll need an initial condition for the voltage across this capacitor, the current through our inductor, and since we're going to have a second order equation, we're going to need an initial condition for our first derivative of this voltage as well. Okay, so we'll go through the process of getting those things. All right, so at t equals 0, this switch closes. So we'll get conditions before the switch closes, before t equals 0, right? So let's start with a current through this. Let's call it IL. At t equals 0 minus, which just indicates right before the switch closes. So we can see that, I guess a quick way of putting it is that before the switch closes, this circuit over here, there's no power source. So, and it's been sitting forever. So we know that everything will have to be discharged. Nothing has ever been charged, put it that way. So we see that without this half of the circuit, no current flows there, right? And no current's flowing, that means no current's flowing in either of these. That means the voltage is also 0. So that gives us pretty quickly the initial value of this current and the initial value of this voltage. Now, so IL at 0 minus is equal to 0. And VC, or what we're going to call V1 at 0 minus, is also equal to 0. Okay, now so we can use characteristics of these two elements here to find these values right after the switch closes. So we know that the current through an inductor can't change instantaneously. We also know that the voltage across a capacitor can't change instantaneously. So these are their values right before the switch closes, and since they can't change in that instant in time, it's going to have to be the same right after the switch closes. So we're going to go, this is equal to IL at 0 plus, which is the instant after that switch makes contact, and this is equal to V1 at 0 plus. Okay, so now we have a couple initial conditions, and we know they're true on both sides of this event right here. So Now let's try to find an initial value for the first derivative of this. So, using this little equation right here, we can see that the current through a capacitor is equal to the capacitance times the time derivative of the voltage across it. So, if we can solve for the value of IC at t equals 0, then we can get an initial value for that derivative, right? So, let's see what, in the instant that this switch closes, let's see if we can figure out what IC would be. So this switch closes, and we know that right after that switch closes, IL is equal to 0, right? Right after that closes. No current flows through here. So that also means no current can flow through that, and no current can flow through that. If there's no current coming into this node, no current can be flowing out, right? So that means that IC, the initial value of IC times 0 plus is equal to 0. That also means that your initial value for this voltage across here, the derivative of this voltage across here, since IC is equal to C dV dt, this is going to equal to C dV1 dt. Now, the only way for this equation to work is if dV1 dt at t equals 0 is equal to 0. So there's our initial value for the voltage across here, the derivative of the voltage across here. Now, it just so happens from the way the circuit functions that this value is 0, but it's important. It's not always going to be 0. You still have to do out the math and get that. All right. So now we can use rules like KVL and KCL. Those rules are always valid for all instance in time, everything. So we're going to set up a differential equation using those. So let's do KVL around this loop. KVL says that, So KVL says that the sums of the voltages around this loop are going to equal 0 all the time, regardless of what's going on in the circuit. So we can sum the voltages. We'll have negative 8 volts from that source, that's constant. We'll have plus VL, which is the voltage across this inductor, plus VR, which is the voltage across this resistor. But one of the first things we said is that VR is equal to VC is equal to V1, which is what we're solving for. So we're going to say that, we're just going to call that V1. So this equation right here is true all the time. But we're going to need a second equation too. So we don't have to stick with KVL. This is how we got this, but we can use KCL to get another equation that's true. So let's use that. Okay, so let's do KCL at this node. Now this KCL says that all the currents flowing into the node sum to 0, or another way of saying that would be the currents flowing in equal the currents flowing out. Alright, so we have IL assigned flowing in, so we'll just say that IL is equal to IR plus IC. So this is also always true. So we can use these equations to set up a differential equation, right? Because we can get these little terms right here in terms of derivatives. So let's say that IL, we know that we know that the voltage across L is equal to L di dt. But we want an expression for IL. Right? So to get this equal to IL, we're going to have to integrate this. We're going to have to integrate both sides. So we can say that IL is equal to 1 over L. And this is going to be a shorthand kind of thing. You have to take into account your initial values, but you'll see we're just going to clear this integral in a minute. So 1 over L times the integral of VL dt. That's equal to IL. That is what IL equals to. Okay, now I'm going to finish this. All that is equal to IR plus IC. But let's see if we can get these two terms in terms of our voltage that we're trying to solve for. So IR, we know that current through resistor is just equal to the voltage over the resistance, right? So we can say IR is equal to V1 over R. So that's the IR term. And now for our IC term, we know that the current through a capacitor is equal to C times the derivative of the voltage across it. So we're just going to write that. We're going to say that IC is equal to C times d VC, but VC is also V1. So we're going to write V1 dt. All right. So this is our differential equation, but we can see that we have two variables in this differential equation. We have V1, which is what we're after, and we have VL. But we can also see that we have a little equation here we can solve for V1 in terms of VL, basically. So eventually we're going to do that and substitute that in. All right, but we're going to rewrite this equation so that it doesn't have an integral in it. So this equation right here becomes, if we don't want this integral, we have to take the derivative of it again, right? So the derivative of this whole thing is going to tell us that 1 over L times VL is equal to 1 over R times, see, we differentiated this. So this is going to become the first derivative of V1. And then we're going to have C times the second derivative of V1. So that's still a valid equation. All we did was take the derivative of both sides of our first equation. And we still have two variables. But from this little equation we wrote here using KVL, this can solve to VL is equal to 8 minus V1. Right? That's just a rearranging of that equation. So where we have VL here, we can just substitute 8 minus V1 into there. So we have 1 over L. 1 over L times 8 minus V1 is equal to 1 over R times our first derivative plus C times our second derivative. Okay, so now we have a differential equation that only has one variable in it, that variable being V1, which is the voltage we're looking for. So we're going to rearrange this to make it a little bit clearer here. We like for, when we go to solve differential equations, we like for them to go in order of, be set up in order of highest to lowest derivatives. So we're going to divide through this equation by c. That'll get rid of that c, and it'll put it down here in these two terms. And then we can write that and now we have a differential equation where our derivatives are in decreasing orders, and we have a constant term here. So we're going to use methods from differential equations to solve that equation. That's our definite differential equation, right? So something we know from differential equations is that your general form of your solution is going to equal your homogeneous solution, which is the solution to the equation that has these derivative terms set equal to 0. That's your homogeneous equation. Let's just say this. So v1 of t is going to equal to our v1, our homogeneous of t, plus a particular solution, which is any one value of v1 that we can pop in there to make it true. So let's call that v1 particular of t. Okay, so our general solution is going to be a sum of these two things. So let's look for a particular solution. Now, it might not be evident right off the bat, but let's say that we put a value of v1, a constant value of v1 in there. What that would mean is that these two derivative terms would go away because the derivatives of a constant value are 0. So then we'd just be left with the equation from here over, right? So what value could we pop in for v1 that would make this part of the equation true? And we could see that if v1 is equal to 8, then this part of the equation would hold true, right? Because these would just cancel and we'd have 8 equals 8. So our v1, our particular solution, is equal to 8 volts. Now, another way of getting that would be to see that our source voltage is 8 volts. That just happens to be our source voltage. And once this circuit settles down again, this would be our value. So this is also known as the V steady state. All right, excellent. So we have a particular solution for our differential equation, and now we're going to come up with a homogeneous solution. So the homogeneous solution is the solution when our differential equation is set to 0. So we're going to write that out. Also, we're going to put definite values in for our terms, our coefficients, 1 over RC and 1 over LC. We have the values for those from our circuit, so 1 over RC is equal to 6. And 1 over LC is equal to 5. Now, for our homogeneous equation, this is all set to 0. So, to get the solution for this, we're going to find what is called the characteristic equation of our differential equation. To get the characteristic equation, we're going to call derivatives, we're going to assign a variable to a derivative, and then we're going to use powers of that to indicate powers of derivatives. So let's call it S. So your second derivative would be S squared. Your first derivative would be S. So we're going to write S squared plus, you keep these coefficients, plus 6S plus 5, but our S indicates a derivative. This is the 0th derivative of v1, right? So it's just going to be S to the 0 or just 5. Now we set that equal to 0. Now there should be a couple different values of S that make this equation true. It would be called the roots of this equation. So using the quadratic formula, we can get the roots of this equation. From the quadratic formula, we'll get S is equal to, say, -6 plus and minus the root of 6 squared, which is 36, minus 4 times 1 times 5, so minus 20, and all of that over 2 times 1. So what this is going to give us is that S is equal to -1 and S is equal to -5. So, without going into exactly why, these roots right here that satisfy this equation they will give us our general solution, or they'll give us our homogeneous solution. So this homogeneous solution is going to have the form an arbitrary constant times e to the s1 t plus another arbitrary constant, we'll call it b, times e to the s2t so that's going to be our homogeneous solution right there. So we have two values of s, our roots. We'll put s1 equals -1 and s2 equals -2, and that's our homogeneous solution. Now our general solution is the sum of our particular solution and our homogeneous solution, so we're going to write that down here. We're going to write v1 of t in general is equal to our particular solution, which is 8 volts, plus our homogeneous solution we'll leave our coefficients undetermined for the time being. And S1 is equal to -1 plus e to the S2, which is equal to -5. So that is our general form of our solution. Now, we also know from differential equations that we solve for the values of these constants using our initial conditions. So, let's see what our initial condition for V1 is. We already solved for that. We know that V1 at t equals 0 is equal to 0. So, we can substitute t equals 0 into this equation and set our result equal to 0. So we're going to say that at t equals 0, this constant term stays. And then at t equals 0, these exponential terms become 1. So we're going to have So there's one equation we can use to solve for our constants, but we still have two unknown constants. So we need another equation. So we also have an initial value for the derivative of this, of v1 at time equals 0. So what we're going to do is we're going to take the derivative of this entire equation and set that equal to whatever our initial condition is. So we're going to say that the constant term will go away, just be equal to 0. This term, when you differentiate it, becomes that. And when you differentiate this term, it becomes okay, so this is equal to the derivative of that voltage, of our voltage. And we know the value of this at t equals 0. We said that dV1 at t equals 0 is equal to 0. So now we can set this equation right here equal to 0. This is equal to 0 at t equals 0. That's the important part. So we substitute t equals 0 into this. Our exponential terms become 1, and that gives us negative a minus 5b is equal to 0. Now there's our second equation that we can use to solve for this. So we're going to say, let's just do the algebra here. We'll say that a is equal to 8 minus b from this equation. Nope, that's not right either. A is equal to negative 8 minus b, right? And we can just substitute that in for a down here. So we'll have negative b. Did I do that wrong? All right, so we have negative 4b is equal to 8. Is equal to negative 8. That means that b is equal to 2. So we have a value for b. We'll substitute b equals 2 back up into this equation, and we'll get that a is equal to negative 10. So now we solve for values of these constant terms here in our general form of our differential equation. So to get our final answer, we'll substitute those values into our general form. So we're going to get V1 of t is equal to 8, it's equal to 8 volts, plus A, but A is equal to negative 10. So we're just going to write minus 10 times e to the negative t, plus B, which is 2, times e to the negative 5t. And that's our solution.